So hello, my name's Isaac. I'm a machine learning scientist at Zendesk. For those who don't know, Zendesk is a customer engagement software company, and my team is working on ML-powered features for quality assurance that see millions of conversations a day. And in my free time, I help maintain the Massive Text Embedding Benchmark, and we call it MTEB. You'll hear it quite often during the talk. It's an open source embedding model evaluation framework, which is heavily related to what I wanted to talk about today. So embedding powers search. Embedding models power search, RAG, clustering features, and are really core components for today's machine learning services. Who here has used embedding models before? OK, most of the room. We have a small room, but most of the room. So we use benchmarks usually to compare models against other models in apples to apples setting and assess how good they really are across the same set of tasks. So if you've been working on, say, coding agents, you might be familiar with SWE-bench, which measures how well LLMs can handle real-world software engineering tasks, like fixing bugs or improving code. If you worked on vector DBs, then you might have seen the vector DB bench, which evaluates performance and cost effectiveness of vector DBs. And if you worked with embedding models, you might have likely heard of BEER on the bottom right and also MTEB on the top right. And often what makes a meaningful benchmark is that it should be challenging, accessible, and reproducible. And what that really means is that something that's not easy, for instance, not any tasks whose state-of-the-art are close to getting almost perfect scores. So MNIST, the digital handwritten digit recognition data set is not one of those. For accessible, that means anyone can run it with any open data or setup. And for reproducible, ideally with the same data, the same code and same conditions, we get the same results. And to help us get a better idea, prepared a few real-life examples of human benchmarks for us. Who is based in the UK here? OK, that's most of the room. So this might resonate well. What happens at 9 a.m. on Saturdays? No one? Park runs? Yeah, maybe? So park runs is like a 5K run in the park nearest to you. That's for sure challenging because it's a time 5K. Anyone can go. So I'd say if your fitness level is the same and you go to the same place, then ideally you get the same time within a margin. OK, and who has gone to school in the UK? Some, OK, half the room. Then you might be familiar with GCSEs, or they call it different things in different countries. These exams are taken by, I guess, 14 to 16-year-olds every year, but they are not the same every year. So I would say they're not that reproducible. And finally, who here has done a job interview before? OK, yeah, everybody. Awesome. Those are definitely not that accessible because you're handpicked and also not that reproducible. So back to embedding models and embedding benchmarks. MTEB is a popular open source text embedding model benchmark. And when it started out in 2022, it covers around 58 data sets across 8 different task categories, like retrieval and re-ranking. It's comprehensive, which makes it challenging. It's open to the public, which makes it accessible. And it features a leaderboard that shows each model's performance and ranking on that benchmark. And what would happen is creators of new models would run the benchmark and then report their own results. That sounds simple, right? Well, not really. So when we try to verify those results, often we can't. And why is that happening? Is that something with the model? Is that something with the benchmark? Am I using a different version of the data set or a different version or a checkpoint of the model? Something changed in the code? Let's take a look at the obvious things that would go wrong. Fortunately, MTEB keeps track of all the relevant versions. So by that, we mean, for example, dataset versions on the right side, where we pin specific Hugging Face revisions. On the left side, on the model side, we will also pin checkpoint versions or API versions. For the code, for the MTEB repository, we follow something like semantic versioning to track changes. And also, we collect all the metadata that is required for reproduction. MTEB also keeps track of these versions in the result object. So whenever you run you run the eval pipeline, you get a result JSON file, and that is everything you likely need. So on paper, everything should be reproducible. But for some reason, it ain't. So let's find out what the issue is. So today I want to dig a bit into why reproducibility in embedding benchmarks is hard, especially in the current dataset and model trends. What we've learned from maintaining MTEB for the last year, what's actually working, and what still needs fixing. So for the first one, so far we have talked about how to make benchmarks reproducible on paper, fixing versions and so on. But that's only half the problem. The other half is really making it possible in practice. So reproducing benchmark results that involve big models and big data sets require a lot of compute resources, even if everything is technically versioned and correct. So let's take a look at some numbers. OK, not a fan of dad jokes, I see. Real numbers. When we take a look at the MTEB English benchmark, there's an increasing number of the top-ranked models that have multiple billion parameters. And these are not cheap, right? One of the embedding model papers from last year reported how long it took to run the full English benchmark on its models. This is a particular 7 billion model called LLM to VEC from Mila, from Montreal. And that almost takes 2 full days nonstop on one of these Amazon AWS P4D instances. Can anybody guess how much that translates to in dollars? Just like a guess? Hundreds, maybe? No, thousands? OK, we get more thousands than hundreds. That's close. So actually around $1,800 when we look at on-demand pricing. Or if you have $200K to shell out to reserve this instance for a year, you can run this for $1,000, which is a bargain. It's starting to sound like you need a cloud budget to run these things and just to reproduce benchmark results, let alone training them. And it's not just the models that are big. The data sets are getting bigger as well. One of the co-authors from the same paper pointed out that the largest data set from MTEB English was called MS Marco. And this is a retrieval task which features a corpus of almost 9 million rows, over 500,000 queries. So this takes 7 hours on the same instance that we saw before, which translates to just under $300 to run. And beyond big models and big data sets, critiques on current benchmarks suggest that they are lacking in multilingual data and also domain diversity. So to help make benchmarks more realistic and more challenging, we want more languages and more domains that are included in the coverage, which actually means more tasks to be run. And this actually becomes quite a significant feat to reproduce any large model results on any benchmarks with any large data sets or a large number of data sets. And it seems like we're in a bit of a pickle, and we're stuck in a loop. We start with the orange star there, from wanting to cover more domains and languages. So we want to include more tasks. But in doing so, we also don't want to spend too much on compute. So we actually want to remove some tasks. And then coming back to the top here, if we don't include enough coverage, then it's not challenging enough, and that people might not use the benchmark as much. And then we go back to the beginning where we want to be more realistic and challenging, so we include more tasks. So how do we get out of this loop? And this is exactly something we explored in one of our recent papers when we were looking to expand MTEB English into a new multilingual benchmark that covers many more languages. A big part of the bottleneck we discovered in eval was inference. So we can just run fewer examples. And the key here is to figure out which samples to run. And thanks to previous literature, there are a few tricks we can use. The first easy one is stratified subsampling, and that is one of the recommended defaults for classification datasets. So let's look at what other tricks we can use for other tasks, like clustering. So clustering, instead of encoding 100% of the dataset, we now encode 4% of the dataset. And we would then sample without replacement 10 different sets, and then do k-means, and then average the scores and report that. That actually yielded around 16 times end-to-end speedup, which is amazing for saving resources, and that still maintained rank when we looked at correlations. For retrieval, we randomly selected 1,000 queries from these bigger data sets that we have identified, and then we kept the documents, only top 250 documents per query. And that actually led to a 20 times reduction for one of the bigger data sets. And then for a task called by-text mining, which is often seen in translation, we would cache the embeddings because some of the same sentences appear quite often when they're shared across different language pairs, like English to Farsi, English to Russian, and so on. And in one of the datasets called Flores, when you look at the English sentences, there used to be 400K, and now we just encode 1K. So this is great. And at the same time, we might not want to run every single task. We want to choose just the ones that give us the biggest bang for the buck. So in our paper, what we did was we initially gathered over 500 tasks and then dwindled it down step by step. We remove a few things like machine translated data sets, those that don't have specified licenses, or any highly domain-specific data sets for the multilingual benchmark. And then after that, once we get to around 300, we look at a representative selection of models. So some large ones, some medium ones, some small ones. And then we run the subset, and using the scores, we iteratively remove the most predictable tasks. And we also keep a few just for language diversity, and we make sure that we don't eliminate any language from any of the task types. And that we repeat that until we cross a certain threshold and ended up with around 130 tasks, all the way from 550. And so we also repeat that for the English benchmark. And as a result, we ended up with a new English benchmark that uses only 2% of the original number of documents. And the number of tasks also went from 50-something to 40. And that has some tangible runtime implications. So on the right side, the runtime for a 7 billion model is now 3 hours, even though it's on a different GPU. I've taken a quick screenshot on RunPot to check pricing as a back at the napkin math. Now it's about $10 instead of the original 1,800. And what is implied also is that it retains relative model ranking, which was important when we were creating this. So that was data sets. For the big model problem, the new multilingual benchmark actually gave us some insights. The key here is to recognize that the world is inherently multilingual. And embedding models that are pre-trained in a more multilingual setting can likely yield similar performance or often outperform much bigger ones. So let's take a look at the multilingual benchmark again. And on the right there, we see a model called Multilingual E5 Large Instruct that is around 12 times smaller than the 7 billion model on the right there. But it performs just as well. And this really challenges the assumption that bigger is always better. And it shows that with the right training setup, smaller models can be highly competitive and still be relevant, especially across multiple languages. And let's zoom out a tiny bit. It also reviews some notable performance gaps in mid-resource languages. So if you look at French, to the right of French, essentially, when there are fewer than 300 million speakers, we see that the multilingual 7 billion models start to be outperformed by much smaller models that are around 500 million parameters. When it's apples to apples like this, it becomes clear that there are better base models that are relatively lightweight and are still competitive in real-life settings. So this really brings us back to a fundamental question about reproducibility. If a benchmark is theoretically reproducible, but practically impossible to run, is that really reproducible? And I think we're learning that accessibility is not really separate. It's more of a prerequisite for reproducibility. So now we've tackled the big data model problem. And there's another challenge that is, here's a hint. It's quite subtle, and it can completely change your results with just a few words. What do you think contributed to this difference in score here? Okay. It's prompts. So this second big challenge we found is related to a special variant of embedding models that are instruction tuned. Turns out embedding models can also leverage prompts to boost performance, but these models actually rely on prompts for the performance, which means things could go badly if you use different prompts or if you don't provide a prompt. So even if you have the same model, same data, your results may vary just because of one missing sentence. The first time we saw this kind of model was around December 2022 from a model called Instructor. Since then, more and more instruction-tuned embedding models have come out, and we can kind of use citation count as a proxy for popularity. These type of models are often trained with instructions that are specific to each training set. So in the example here, for example, it will say retrieve documents that can help answer this question, and then the query itself. And in practice, how prompts are used varies by the model, and generally there are a few different main flavors. The first one being fixed prefixes, so it doesn't matter what data set you use. You're just going to put query in front of query, passage in front of your passage, your corpus passages. Some might differ by task type, so a clustering one might be different than a retrieval one. And also, it might differ by the task or data set. So for instance, this one is very tailored to Reddit posts. And this kind of quickly become a bit more tailored to the task, and like what we saw before, tailoring to specific domain papers or posts or a given web search query. So we need to keep track of these as well. And so how MTEB does that is with task-specific prompts, they are stored along with the rest of the task metadata. So along with all the what main metric this is, what language this data set is, we also have a particular prompt for that. And then on the model side, some models, like on the top, will use a template So that task-specific prompt we saw from before would just be inserted there. And other model-specific prompts, like on the bottom, they live with other model metadata. So these would then be also committed to the repo, and they're also version controlled. So I've talked about all this stuff. Does that really work? The short answer is yes. We did find the missing points from the scores, which is great. And sometimes the differences can be small. Sometimes they could be quite huge. But that said, prompts also remain as quite a common issue when introducing new models to the benchmark, even for maintainers. But at least we're learning these lessons in public, so everybody can see our struggles as well. And just as we're getting the hang of text embedding models, the field is rapidly getting multimodal and going beyond text. So we found that each new modality has bring its own reproducibility challenges and some familiar ones in new disguises. When we extend our benchmark to handle different modalities like image, audio, or even multimodal input, we ran into issues that go beyond just adding data sets. Each input type has its own quirks. So for example, for image, there's a notion of pre-processing that crops and resize the image. So don't forget that. For text and image, where one query is the combination of the two, how that is combined can also be model dependent. So it could be the embeddings could be concatenated. You could simply feed that into the model, and there's already a learned fusion or some sort of token level mixing for VLMs. There's also some truncation limit that we don't often see with current day text embedding models with huge context lengths. So for example, famously, the CLIP model has a 77 token limit. And for audio, it's sampling rates and padding. And these small details could easily trip up and cause results not to be matching. And inputs aside, models can also be a source of variance as well. And we want to load the right model in the intended way. In this example, we see OpenClip and Visual BGE. These are loaded in different ways, with different parameters, with different libraries. So we can't just pass the same parameters to both models and call it a day. With the same models here, they call, encode, predicts in a different way as well. So OpenClip uses encode image, and Visual BGE uses just encode, sort of like in sentence transformers. What this means is that this adds another small layer of complexity to reproducing results and potentially another source of discrepancy. And then a third way we could kind of fail, which is super not obvious, is related to normalization. And we see this in both text and image embedding models, where sometimes this step is explicitly needed and sometimes it just isn't. So it really depends on the model, and it's in the details. And sometimes we don't get it right, and we need a gentle nudge from the model creators. It just says, we don't normalize the embeddings. And also, just like the text embedding models, VLMs and image embedding models can also be huge. They could be as big as 8 billion parameters. This is on the image benchmark that came out a few months back. So with this, what can we do? For the model implementation problem, we can standardize the model interface. It's not super exciting. You just essentially say, here are the inputs that we expect, and here are the outputs, and here's the methods that we would like you to call. And it looks kind of like this, where we say, we want a specific method for image embeddings, text, and also the combined embeddings. So ideally, this would help eval much smoother, and also we can plug in new models without having to tweak the code or rewrite any part of the pipeline. And from the user's perspective, which hopefully is all y'all, is that the only difference in running a different model or a different task is in the names. And there's nothing else that really changes, and we think it really simplifies things. And so researchers or any practitioners could focus on comparing model performance or other priorities rather than debugging eval infrastructure. Another thing that the image benchmark reveals is that some smaller models, like in the text counterpart, can achieve very similar performance compared to the big ones. And again, on the top right corner, we see a model that is almost 10 times smaller than the 8 billion model, performs pretty much just as well. Some of you may know that's called one of the siglib variants from Google. And again, this benchmark draws light onto more efficient and effective strategies for training embedding models. And this is not just for academic curiosity, but also for practical applications when compute and latency would matter. And for someone who would use this in a production case, then the trade-off is quite clear, right? Like to give 1% performance for a much smaller model that could support higher throughput and require much less compute resources. So we have identified the problems and some solutions. And this is where my friend Duarte would put his "so what" slide. And I think that is a fair question to ask. Why should you care? What's in it for you and the broader community? I think we slightly hinted at that before with the way we ran different modalities with pretty much the same command line interface. The first and foremost is that we've already done a lot of the work for you and done a lot of the building, the learning, and all you need to do to essentially do all that is do pip install MTEB. And this hopefully saves you time so you could focus on other meaningful work like attending your 50th Zoom call of the day. And to run anything we've seen so far, it's as easy as one line of code. And as long as their sentence transformers compatible, it doesn't need a model implementation. So this would be the exact command you run for the Qwen 3 embedding model, which only came out on Thursday, this Thursday. And we have a lot more examples on our docs page, like how to run entire benchmarks, actually like the second line, and how to add your own model and how to add your own data set. And thankfully, the community also acknowledges the importance of a unified eval framework that prioritizes reproducibility. So, we see academic and industry labs use MTEB as their go-to framework. These are some screenshots from LinkedIn that we saw within the last couple months. I think these are the static embedding folks, and then we see Google DeepMind was using the same benchmarks as well. And we also starting to see some prominent benchmarks see this framework as more of a long-term solution for maintenance. For Manuel, he is finishing his PhD, so he wouldn't have a capacity to maintain his visual document retrieval benchmark, and he has approached MTEB so that we could transition that as part of the framework. And so that has been done. You can also do the whole MTEB run-b and run the entire benchmark in one line of code. So it's I don't want to paint a too rosy picture. Of course, MTEB has made reproducibility better, but we haven't solved everything. And for one, a big topic that we haven't spent much time on is hardware. We know that different hardware likely introduces some variance. Specifically, there are known issues with floating point non-determinism in GPU operations. And maybe it's as easy as adding this one line of code, but there might be more than meets the eye. And if you have any experience in this, we would love to chat. And we mentioned before that we pin dataset versions, but public datasets aren't static artifacts like we pretend they are. And especially when we rely on Hugging Face datasets that are in other people's accounts. And when this happens, that is often outside of our control. The datasets might be taken down for many different reasons. In this example, we found a Norwegian summarization dataset that was no longer available. And so this dataset was used in the Scandinavian benchmark and the multilingual benchmark. We're then forced to bump the versions on those. So one of our current efforts is to start rehosting these datasets that are on our most popular benchmarks under the MTEB organization on Hugging Face. As for the other aspects, there's something that we don't talk about enough, like how benchmarks change how the models are built. And so once MTEB became popular, we're starting to see models that are clearly optimized for this benchmark. And this is not necessarily bad, but it really creates a feedback loop where models get better at the benchmark, but we don't know if they are really better at the general capabilities. So it's like teaching to test in education. And this kind of benchmark grokking doesn't really necessarily translate to good general performance. And so to address this, we have tried to encourage model contributors to disclose training datasets, and we compute a zero-shot score to quantify the distributional overlap. This metric really offers a really coarse estimate of how in-domain or out-of-domain a model is with respect to the benchmark. So for example, Quan3, we're not sponsored, but they're just really recent, has a 95% zero-shot score, which means it's only trained on about 5% of the benchmark's training splits. This is still something we're trying to figure out, but next time, if you can't reproduce a benchmark result, don't just shrug and move on. We encourage you to file an issue, share your config, share what broke, because the benchmark that works for everyone starts with the edge cases that break for someone. Thank you very much.